Section 1.4, Measurements. By the end of this section, you will be able to 1. Explain the process of measurement. 2. Identify the three basic parts of a quantity. 3. Describe the properties and units of length, mass, volume, density, temperature, and time. 4. Perform basic unit calculations and conversions in the metric and other unit systems. Measurements provide much of the information that informs the hypotheses, theories, and laws describing the behavior of matter and energy in both the macroscopic and microscopic domains of chemistry. Every measurement provides three kinds of information: the size or magnitude of the measurement, a number, a standard of comparison for the measurement, a unit, and an indication of the uncertainty of the measurement. While the number and unit are explicitly represented when a quantity is written, the uncertainty is an aspect of the measurement result that is more implicitly represented and will be discussed later. The number in the measurement can be represented in different ways, including decimal form and scientific notation. Scientific notation is also known as exponential notation. A review of this topic can be found in Appendix B. For example, the maximum takeoff weight of a Boeing 777-200 airliner is 298,000 kilograms, which can also be written as 2.98 multiplied by 10 to the power of 5 kilogram. The mass of the average mosquito is about 0.000025 kilograms, which can be written as 2.5 multiplied by 10 to the power of negative 6 kilogram. Units, such as liters, pounds, and centimeters, are standards of comparison for measurements. A 2-liter bottle of a soft drink contains a volume of beverage that is twice that of the accepted volume of 1 liter. The meat used to prepare a 0.25-pound hamburger weighs 1/4 as much as the accepted weight of 1 pound. Without units, a number can be meaningless, confusing, or possibly life-threatening. Suppose a doctor prescribes phenobarbital to control a patient's seizures and states a dosage of 100 without specifying units. Not only will this be confusing to the medical professional giving the dose, but the consequences can be dire. 100 milligrams given 3 times per day can be effective as an anticonvulsant, but a single dose of 100 gram is more than 10 times the lethal amount. The measurement units for 7 fundamental properties, base units, are listed in Table 1.2. The standards for these units are fixed by international agreement, and they are called the International System of Units or SI units, from the French, Le Système International d'Unités. SI units have been used by the United States National Institute of Standards and Technology, NIST, since 1964. Units for other properties may be derived from these 7 base units. Base units of the SI system. Property measured. Name of unit. Symbol of unit. 1. Length. Meter. M. 2. Mass. Kilogram. Kg. 3. Time. Second. S. 4. Temperature. Kelvin. K. 5. Electric current. Ampere. A. 6. Amount of substance. Mole. Mole. 7. Luminous intensity. Candela. CD. Table 1.2. Everyday measurement units are often defined as fractions or multiples of other units. Milk is commonly packaged in containers of 1 gallon, 4 quarts, 1 quart, 0.25 gallon, and 1 pint, 0.5 quart. This same approach is used with SI units, but these fractions or multiples are always powers of 10. Fractional or multiple SI units are named using a prefix and the name of the base unit. For example, a length of 1,000 meters is also called a kilometer because the prefix kilo means 1,000, which in scientific notation is 10 to the power of 3, 1 kilometer, equals, 1,000 meter, equals, 10 to the power of 3 meter. The prefixes used and the powers to which 10 are raised are listed in Table 1.3. Common unit prefixes. Prefix. Symbol. Factor. Example. 1. Femto. F. 10 to the power of negative 15. 1 femtosecond, fs, equals 1 multiplied by 10 to the power of negative 15 second. 2 pico, p, 10 to the power of negative 12. 1 picometer, pm, equals 1 multiplied by 10 to the power of negative 12 meter. 3 nano, n, 10 to the power of negative 9. 4 nanograms, ng, equals 4 multiplied by 10 to the power of negative 9 gram. 4 micro, mu, 10 to the power of negative 6. 1 microliter, mu L, equals 1 multiplied by 10 to the power of negative 6 liter. 5 milli, m, 10 to the power of negative 3. 2 millimoles, mmol, equals 2 multiplied by 10 to the power of negative 3 moles. 6 centi, c, 10 to the power of negative 2. 7 centimeters, cm, equals 7 multiplied by 10 to the power of negative 2 meter. 7 deci, d, 10 to the power of negative 1. 1 deciliter, dl, equals 1 multiplied by 10 to the power of negative 1 liter. 8 kilo, k, 10 to the power of 3. 1 kilometer, km, equals 1 multiplied by 10 to the power of 3 meter. 9 mega, m, 10 to the power of 6. 3 megahertz, mhz, equals 3 multiplied by 10 to the power of 6 hertz. 10 giga, g, 10 to the power of 9. 8 giga years, g year, equals 8 multiplied by 10 to the power of 9 years. 11 tera, t, 10 to the power of 12. 5 terawatts, tw, equals 5 multiplied by 10 to the power of 12 watt. Table 1.3. Link to learning. Need a refresher or more practice with scientific notation? Visit this site. http://openstackscollege.org/l/16 notation. To go over the basics of scientific notation. 1.4.1 SI base units. The initial units of the metric system, which eventually evolved into the SI system, were established in France during the French Revolution. The original standards for the meter and the kilogram were adopted there in 1799 and eventually by other countries. This section introduces 4 of the SI base units commonly used in chemistry. Other SI units will be introduced in subsequent chapters. A. Length. The standard unit of length in both the SI and original metric systems is the meter, m. A meter was originally specified as 1/10 million of the distance from the North Pole to the equator. It is now defined as the distance light in a vacuum travels in 1/299,792,458 of a second. A meter is about 3 inches longer than a yard, figure 1.23. 1 meter is about 39.37 inches or 1.094 yards. Longer distances are often reported in kilometers. 1 kilometer equals 1,000 meter equals 10 to the power of 3 meter. Whereas shorter distances can be reported in centimeters. 1 centimeter equals 0.01 meter equals 10 to the power of negative 2 meter, or millimeters. 1 millimeter equals 0.001 meter equals 10 to the power of negative 3 meter. Figure 1.23. 1 inch equals 2.54 centimeter. 1 meter equals 1.094 yard equals 39.36 inches. Figure 1.23. The relative lengths of 1 meter, 1 yard, 1 centimeter, and 1 inch are shown, not actual size, as well as comparisons of 2.54 centimeter, and 1 inch, and of 1 meter, and 1.094 yard. B. Mass. The standard unit of mass in the SI system is the kilogram, kg. A kilogram was originally defined as the mass of a liter of water, a cube of water with an edge length of exactly 0.1 meter. It is now defined by a certain cylinder of platinum-iridium alloy, which is kept in France, figure 1.24. Any object with the same mass as this cylinder is said to have a mass of 1 kilogram. 1 kilogram is about 2.2 pounds. The gram, g, is exactly equal to 1 over 1,000 of the mass of the kilogram, 10 to the power of negative 3 kilogram. Figure 1.24. This replica prototype kilogram is housed at the National Institute of Standards and Technology, NIST, in Maryland. Credit: National Institutes of Standards and Technology. C. Temperature. Temperature is an intensive property. The SI unit of temperature is the Kelvin, K. The IUPAC convention is to use Kelvin, all lowercase, for the word, K, uppercase, for the unit symbol, and neither the word degree nor the degree symbol, degree. The degree Celsius, is also allowed in the SI system, with both the word degree and the degree symbol used for Celsius measurements. Celsius degrees are the same magnitude as those of Kelvin, but the two scales place their zeros in different places. Water freezes at 273.15 K, 0 degrees Celsius, and boils at 373.15 K, 100 degrees Celsius, by definition, and normal human body temperature is approximately 310 K, 37 degrees Celsius. The conversion between these two units and the Fahrenheit scale will be discussed later in this chapter. D. Time. The SI base unit of time is the second, s. Small and large time intervals can be expressed with the appropriate prefixes, for example, 3 microseconds equals 0.000003 s equals 3 multiplied by 10 to the power of negative 6, and 5 megaseconds equals 5 million seconds equals 5 multiplied by 10 to the power of 6 second. Alternatively, hours, days, and years can be used. 1.4.2. Derived SI units. We can derive many units from the 7 SI base units. For example, we can use the base unit of length to define a unit of volume, and the base units of mass and length to define a unit of density. A. Volume. Volume is the measure of the amount of space occupied by an object. The standard SI unit of volume is defined by the base unit of length, figure 1.25. The standard volume is a cubic meter, m cubed, a cube with an edge length of exactly 1 meter. To dispense a cubic meter of water, we could build a cubic box with edge lengths of exactly 1 meter. This box would hold a cubic meter of water or any other substance. A more commonly used unit of volume is derived from the decimeter, 0.1 meter or 10 centimeter. A cube with edge lengths of exactly 1 decimeter contains a volume of 1 cubic decimeter, dm cubed. A liter, L, is the more common name for the cubic decimeter. 1 liter is about 1.06 quarts. A cubic centimeter, cm cubed, is the volume of a cube with an edge length of exactly 1 centimeter. The abbreviation cc, for cubic centimeter, is often used by health professionals. A cubic centimeter is equivalent to a milliliter, and is 1 over 1,000 of a liter. Figure 1.25. 1 meter cubed. 1 decimeter cubed equals 1 liter. 1 centimeter cubed equals 1 milliliter. 1 centimeter cubed equals 1 milliliter. 1.8 centimeter is the diameter of a dime. Figure 1.25. A. The relative volumes are shown for cubes of 1 meter cubed, 1 decimeter cubed, 1 L, and 1 centimeter 3, 1 milliliter, not to scale. B. The diameter of a dime is compared relative to the edge length of a 1 centimeter cubed, 1 milliliter, cube. B. Density. We use the mass and volume of a substance to determine its density. Thus, the units of density are defined by the base units of mass and length. The density of a substance is the ratio of the mass of a sample of the substance to its volume. The SI unit for density is the kilogram per cubic meter, kilogram per meter cubed. For many situations, however, this is an inconvenient unit, and we often use grams per cc, gram per centimeter cubed, for the densities of solids and liquids, and grams per liter, gram per liter, for gases. Although there are exceptions, most liquids and solids have densities that range from about 0.7 gram per centimeter cubed, the density of gasoline, to 19 gram per centimeter cubed, the density of gold. The density of air is about 1.2 gram per liter. Table 1.4 shows the densities of some common substances. Densities of common substances. A. Solids. Ice, at 0 degrees Celsius, 0.92 gram per centimeter cubed. Oak, wood, 0.60 to 0.90 gram per centimeter cubed. Iron, 7.9 gram per centimeter cubed. Copper, 9.0 gram per centimeter cubed. Lead, 11.3 gram per centimeter cubed. Silver, 10.5 gram per centimeter cubed. Gold, 19.3 gram per centimeter cubed. B. Liquids. Water, 1.0 gram per centimeter cubed. Ethanol, 0.79 gram per centimeter cubed. Acetone, 0.79 gram per centimeter cubed. Glycerin, 1.26 gram per centimeter cubed. Olive oil, 0.92 gram per centimeter cubed. Gasoline, 0.70 to 0.77 gram per centimeter cubed. Mercury, 13.6 gram per centimeter cubed. C. Gases, at 25 degrees Celsius and 1 atmosphere. Dry air, 1.20 gram per liter. Oxygen, 1.31 gram per liter. Nitrogen, 1.14 gram per liter. Carbon dioxide, 1.80 gram per liter. Helium, 0.16 gram per liter. Neon, 0.83 gram per liter. Radon, 9.1 gram per liter. Table 1.4. While there are many ways to determine the density of an object, perhaps the most straightforward method involves separately finding the mass and volume of the object, and then dividing the mass of the sample by its volume. In the following example, the mass is found directly by weighing, but the volume is found indirectly through length measurements. Density equals mass over volume. Example 1.1. Calculation of density. Gold, in bricks, bars, and coins, has been a form of currency for centuries. In order to swindle people into paying for a brick of gold without actually investing in a brick of gold, people have considered filling the centers of hollow gold bricks with lead to fool buyers into thinking that the entire brick is gold. It does not work. Lead is a dense substance, but its density is not as great as that of gold, 19.3 gram per centimeter cubed. What is the density of lead if a cube of lead has an edge length of 2.00 centimeter and a mass of 90.7 gram? Solution. The density of a substance can be calculated by dividing its mass by its volume. The volume of a cube is calculated by cubing the edge length. Volume of lead cube equals 2.00 centimeter multiplied by 2.00 centimeter multiplied by 2.00 centimeter equals 8 centimeter cubed. Density equals mass divided by volume equals 90.7 gram divided by 8 centimeter cubed equals 11.3 gram divided by 1.00 centimeter cubed equals 11.3 gram per centimeter cubed. We will discuss the reason for rounding to the first decimal place in the next section. Check your learning. A. To 3 decimal places, what is the volume of a cube, centimeter cubed, with an edge length of 0.843 centimeter? B. If the cube in part A is copper and has a mass of 5.34 gram, what is the density of copper to 2 decimal places? Answer. A. 0.599 centimeter cubed. B. 8.91 gram per centimeter cubed. Link to learning. To learn more about the relationship between mass, volume, and density, use this interactive simulator. http://openstackscollege.org/l/16femasvold. To explore the density of different materials, like wood, ice, brick, and aluminum. Example 1.2. Using displacement of water to determine density. This PhET simulation. http://openstackscollege.org/l/16femasvold. Illustrates another way to determine density, using displacement of water. Determine the density of the red and yellow blocks. Solution. When you open the density simulation and select same mass, you can choose from several 5.00 kg colored blocks that you can drop into a tank containing 100.00 liter water. The yellow block floats, it is less dense than water, and the water level rises to 105.00 liter. While floating, the yellow block displaces 5.00 liter water, an amount equal to the weight of the block. The red block sinks, it is more dense than water, which has density, equals 1.00 kg per liter, and the water level rises to 101.25 liter. The red block therefore displaces 1.25 liter water, an amount equal to the volume of the block. The density of the red block is density equals mass divided by volume equals 5.00 kg divided by 1.25 liter equals 4.00 kg per liter. Note that since the yellow block is not completely submerged, you cannot determine its density from this information. But if you hold the yellow block on the bottom of the tank, the water level rises to 110.00 liter, which means that it now displaces 10.00 liter water, and its density can be found. Density equals mass divided by volume equals 5.00 kg divided by 10.00 liter equals 0.500 kg per liter. Check your learning. Remove all of the blocks from the water and add the green block to the tank of water, placing it approximately in the middle of the tank. Determine the density of the green block. Answer: 2.00 kg per liter.